Welcome to a new video about power electronics. In this example, we will discuss the design of a buck converter. We will see how we can step by step create these graphs for this circuit, which is a buck converter circuit, step by step in our calculations, and also verify this in MATLAB Simulink simulations, and also on top of that using the Tina TI SPICE simulation. So we will also compare the two simulation results. So let's look at our objective or outline for this video. The outline will be the first part of this video will be about the open loop calculations. So we will see how the buck converter circuit works in general. We will see the specifications also, and also the component values, and we will talk about the ratings of our calculated components. In the part 1b, we will also see the simulation results. So we will compare it with the calculations. We will do that in Tina TI SPICE and MATLAB Simulink, and we will fine-tune where necessary. And this will be the topics for this video. In the next video, part 2, also divided in two parts, we will calculate the necessary component values for our controller. So we will also look at how we can make the loop stable and select the specific phase margin, and also design the controller circuit. And then again, simulating using the MATLAB Simulink and also Tina TI SPICE, and where necessary we need to fine-tune. Okay, and this part is where we consider in this video. Now let's start with part 1a. Before we look at the details, let's give a short introduction why we need switching voltage regulators. Because the linear voltage regulators function like so has the following issue. This is a transistor which can be switched using PWM signal, and this transistor can be also modeled by a variable resistor as shown here. So we have a DC voltage source, this is controlled by this PWM signal, and we have then a specific output voltage and output current determined by this PWM signal. And this is then a model for that part. You see here that there is a variable resistor R which models this transistor. Now, in order to lower this voltage Vs to VO, you need to burn some power here in this resistor, which is then make this circuit not really efficient. So the output voltage is regulated by adjusting the transistor base current, and the absorbed power is equal to the delivered power minus the power we dissipate in this resistor because of the switching in this transistor. So the power dissipated by the transistor is then given by this, and it is inefficient because there is really too much power dissipated in this transistor. So what can we do? So we can switch here and then go on or off. Why is this switching more efficient than a constant resistor, which is a variable resistor here? Because when the switch is closed, the voltage across this switch will be 0. So since the power is the product of the volts, so the voltage and the current, so it will be then 0 power dissipation. And when the switch is opened, there is no current flow. That means again a power of 0 watts, because you have the volts times 0 amps, so it will be then 0 watts. So there's actually two situations where you have 0 power dissipation in ideal case. We also have a duty cycle situation. So for this PWM signal, you have a part where the switch is closed. That means you have full Vs across the load, considering the switch is ideal. And when the switch is opened, then you have nothing, which is 0. So this is then the switching voltage regulator, and the duty cycle is defined as the T on divided by the T on plus T off, which is also T on over the period. And the average output voltage is calculated using the integral. So you need to integrate from the 0 to the T, so across the full period of this waveform. And that is then the general expression we know from the average value calculations. Now, you need to split your problem in two parts, because this starts at 0 and then goes to dt, and from dt to t. So we actually have now two parts of the integral. First part of the integral is Vs, so the VO will be Vs, but the second part is 0. So we can then cross this out, and you have effectively this expression. And that can be calculated. Since VO is Vs, and you evaluate this integral, you get this now VO is equal to D times Vs. We will see this formula also later for the analysis of the buck converter. So let's jump to the buck converter. The buck converter circuit is shown here. We have two situations where the switch is closed and where the switch is opened. So first one is the switch is closed. You see here the switch is closed. The diode will be reverse biased, so that means the diode is also open, and there will be a current flow here through the inductor to the capacitor and also to the load. And when the switch is opened, the situation is like so, so it is opened, then the diode will be forward biased. Why? Because the inductor current will be circulating, and then diode current will be then forward biased in this fashion, and that is why this diode is also there. So there's a reason for having a diode there. So we have two situations, closed and open. So voltage relationship, voltage current relationship for this circuit for the inductor current is the following. Since the inductor current is periodic, you can say the inductor current at some time is also equal to the inductor at that same time plus a period later or before. And this is the periodicity in the inductor current. For average inductor voltage, we know that this is 0. So the average voltage of an inductor is 0. That means when you integrate the voltage, the inductor voltage, across one period, you need to have 0. The similar is for the capacitor valid, but then for the capacitor current. So that means the capacitor current average is 0, and when you do the integration for the capacitor current, in the same manner, you get also 0. And these two equations are very important for calculating the components values for our buck converter. Let's also look at the switching analysis. When a switch is closed, we know that the VL here, using Kirchhoff's voltage law, is equal to Vs minus the voltage across the load, which is then this. But since the inductor voltage is given by the L dIL dt, so this is from physics, you know, we can also write it like so. So divide the left and right side by the L, and then make the differential part in the delta variation. You get this, and since delta t here is just the dt part, so which is then the switch close part, so d times t, so duty cycle times the period, you get a formula like so. And this is now the formula where you have the delta IL closed form, and this is the expression for the closed form for our inductor. Now, we can also look at the switch open in a similar forms. If the switch is opened, that means this one, then your voltage across the inductor will be the minus of the voltage across the load, and that will be again the same formula for the inductor. And when you work it out in a similar fashion, you get now the delta IL over delta t. Now the delta t is the part where the switch is open, that is then 1 minus the d in parentheses times t, and you have this expression. Again, you can calculate or express now for open situation. Now you have this formula. Now switch closed and switch open formulas are here, and these are now the waveforms for the inductor voltage, inductor current and the capacitor current. At steady state, these two formulas together, or these two expressions for our delta IL, so the peak current of the inductor, will be 0. That means the following: you take this and this expression, add them up, and they will not need to be 0. You can divide out the t over L here, so you get actually this expression. And when you now rewrite this such that you have the VO in terms of the other parameters, you get this expression. And this is also the expression we have seen before in the introduction. Now you see it also from the buck converter analysis. Okay, now let's also look at the circuit equation for the load current at steady state. We can say, since it is steady state, that means there are no variations anymore, the capacitor will behave as an open circuit. So the inductor current will be exact same as the load current at DC or at average. And this is used Ohm's law, which is then output voltage or load voltage over resistor. As said, the capacitor will be 0, the average capacitor current, so that means also from this formula. Peak inductor current, that can be calculated again using these two formulas. And we can use one of these to calculate or express the peak inductor current. So we will, for example, take this or that, it doesn't matter. The maximum inductor current can be calculated using the average inductor current plus the peak inductor current over 2. And now we get this expression because the average inductor current was VO over R from here, and this is now half of the expression here. And again, remember that the switching frequency is 1 over the period. In a similar form for the minimum inductor current, you only have a minus sign here, so the formula is similar. The next part is about the conduction mode, because our buck converter can operate in the continuous current mode or in the discontinuous current mode. What does it mean? Continuous current mode means that your inductor current is always large 0, and that needs to be checked, because that will determine also what the formulas are in order to determine the component values. Now we can check that by setting the minimum inductor current to 0, that is the boundary, which means this expression must be 0, and that is shown here. We can evaluate that this is the inductor value we need minimally in order to stay at the continuous current mode. So if you go, this is the L minimum, so if you go below this value, then you have a discontinuous current mode. Okay. Now, more detail about the output voltage ripple. For that we need to look at the waveform for the capacitor current, which is also here shown for the output voltage as a ripple. And this delta VO, peak output voltage, is related to that capacitor charge and also its current. So the capacitor current is given by the IC, which is this current, is equal to the inductor current minus the output current, which is just using Kirchhoff's current law at this node. And we know that the capacitor charge from physics is Q is equal to C times the voltage across this, which is VO. Now the change in the capacitor charge can be done by using delta Q is equal to C times delta V, assuming that the charge is constant. This is now the expression, and you see here the expression for our peak output voltage. Using this graph, and since we know that the average capacitor current is 0, so this is now leveled at 0, this part, this triangle area, is where the charge is. So we can calculate what that is. This is really geometry. You can see here that is height of the peak of the inductor current over 2, and this width here is the half of the period. So we can say the triangle area is a half times the half of the period times a half of the peak inductor current. That's actually shown here. That can be also written like so. Now we will now use this in this formula. We can also do it actually like T in here, which is 1 over T is then the switching frequency. So the change in the output voltage is then delta Q over C. Let's get this delta Q here in this expression and rewrite this such that here the expression is shown here. Now we know that the delta IL, which is the peak inductor current, was given by this expression in the previous discussion. So we can also substitute that in here, and that will give us this expression. Now, simplifying this form, you get here the VO times 1 minus D over 8 times L C switching frequency squared. So your delta VO, so your peak output voltage, is determined by your duty cycle, the output voltage you want, your inductor value, your capacitor value, and also your switching frequency squared. So this is now, these are the parameters that will affect your output peak voltage. Okay, now you can also write it down in percentage or in a ratio of the peak output voltage over the output voltage itself, and then this is the expression. Or you can also write it down in a form that you have the capacitor required for a specific specification that is actually shown here. Okay, let's now go to the design of our buck converter. For this case, you see here now the design requires an output voltage of 15 volts, output current of 2 amps, so that's actually for these two. And we need to use a DC input voltage of 60 volts. And the maximum percentage peak output ripple voltage, that's given by delta VO over VO, is 0.01. That means we can have only peak error in our output voltage of 1%. That's maximum. So we have 3 specifications. Again, the waveforms here for our inductor voltage, inductor current, and also the capacitor current. So let's look at our solutions. We know that we have a duty cycle for our objective, which is then determined by the output voltage over the input voltage. So that is now calculated like so. You see here 15 over 60 is then 0.25 or 25% duty cycle. The next step is switching frequency. We need to select that. This is really an arbitrary value. If you take a lower switching frequency, then you have less switching losses, but if you have a lower frequency, switching frequency, then the inductor value will be larger, so it can be maybe difficult to prototype that. If you go higher to higher frequencies, it will create lower inductor values, so it is then more practical and also easier to find, but you will have more switching losses. So there is some trade-off, some optimum in some specifications. And this then switching frequency here is just selected at 100 kilohertz. There's also a specification you need to select, so it is also really random. So peak inductor current, in this case I take that as 20% of our average or output current I need. That means 20% of 2 amps will be then 0.4 amps. Again, selected. You can also take 10% or 15%, really it doesn't matter in most cases. Now the first component we need to calculate is the inductor, which is the L. Again, this is from the analysis before. This is the formula now we need to use. We have the required values. We can calculate it will be then 281 microhenries. So we can say that this is the minimum inductor value we need for our design. You can also say let's go a little bit higher in order to create some safety. So let's round it off to 300 microhenries. Then this is then the component we will use. But we have now selected this one instead of 281, so we can see how much peak inductor current then this will create. So we need to recalculate our inductor current peak. Again, using this formula, so rewrite that. That's actually shown here. Using the new inductor value, it will give us 0.375 amps. So it goes down. So larger the inductor value, the lower the peak inductor current. The maximum inductor current, as said before, that can be calculated like so. That will be then 2.188 amps. And the minimum inductor current in the similar form, which will be then 1.813 amps. Okay, and this is, as shown here, larger than 0. So we are in the continuous current mode. Okay. We will move on and go to the next step, which is about the RMS inductor current. This is important for our component ratings, and this is calculated using this formula. You see here in the square root the average value of the inductor current squared plus the part which is due to that triangle. So this is then a peak inductor current over 2 divided by square root of 3 and quantity squared. This is just from the analysis about the RMS value. You substitute here the values, you get almost 2.003, so close to 2 amps. And this is also a part of the rating for our inductor when you select your inductor. Now the inductor is selected, we know also some about the maximum, minimum and RMS currents. So let's go to the next component, which is our capacitor. Capacitor can be calculated using this formula. We know the duty cycle, we know the inductor, we also know the delta VO over VO, and we have also selected our switching frequency, so substitute everything, you get here 3.125 microfarads. So we can say this is the minimum capacitor we need for our ripple voltage specification. You can of course go a little bit higher for safety, but in this case I just selected as exactly as calculated here. Now, one important parameter for our capacitor is the maximum allowed equivalent series resistor, because this will determine your delta VO, your peak output voltage. And since peak output voltage is equal to 1% of the actual output voltage, so that means 0.15 volts, and the output voltage peak is also related to that RC, which is the small letter RC, which is the equivalent series resistor of our capacitor, and that is given by this expression. Since the delta IC, so the capacitor peak value, is also equal to the inductor peak value, inductor current peak value, we can say that this is the value of the equivalent series resistor we can have at max. So 0.4 ohms we can have at max, considering this peak inductor current. And so if you select your capacitor, which is in 3.1 microfarad, for example, you cannot manage this value. You need to maybe go up or go down and then maybe adjust other parameters in order to stay in that vicinity of your output peak voltage ripple. And how about the RMS capacitor current? Now that is calculated using the similar formula as we have done for the RMS inductor current. You see that here again the average capacitor current, and here the part because of the triangle. Since the average is 0, that means this part is 0, and the other part is exact same as before for the inductor current, so that will give us in this case, using the values, 108.3 milliamps. The load resistor, so what do we need minimum here as our load resistor, depends on the output voltage and the maximum output current, and that's given by Ohm's law 15/2, so it will give you 7.5 ohms, and this is the minimum allowed load resistor. If you go down to 7 or 6 ohms, you will draw more current here, so your voltage will be going down. In this case, in open loop configuration, you will not have what you wanted in the specifications. Okay, let's now look at the simulation results using MATLAB Simulink. Okay, now this is the Simulink circuit. So we see here the switch, the DC voltage source, the diode, the inductor, the capacitor and the resistor, and these are the waveforms we will plot from the scope here. You see also some values we measure here, the RMS value for inductor current and also the RMS value for capacitor current. We have calculated for RMS inductor was 2.003 amps, so this is 2.009 in the simulator, so that is fine. And for the capacitor it is 0.108 amps, and in this case, and we have also close to that, so that's also nice to see. Let's also see that shortly in the MATLAB Simulink simulations, but before I dive into that, I will also show you the plots here. So for the steady state value, you see that there's the yellow one, which is output current or load current, and the light blue one is a load current. You see here in the table what the values are. So here in the table you see the values for the labels, and here is almost 2 amps for our output current, which is what we wanted, and also here almost 15 volts for output voltage, so also close to what we wanted. So this is nicely checked. Now moving on to the peak inductor current, which is red one. You see here the peak value here and peak minus, so maximum here and minimum there. Again, the values are shown here. We see here 2.2 amps approximately maximum, and this is then 1.8, so 1.82 amps. And these are close to what we have calculated actually here, so this is also nice. And the peak here is 0.3737 amps, which is close to this 0.375 amps. So this is also checked in this. Going to the peak inductor voltage is the green one. You see here the maximum. Again, we can calculate that using the Vs minus Vo, which is 16 minus 15, 45, and the minimum will be then minus Vo will be then minus 15. Now, if I look at the label 1 here from the table, give us here 54.04 volts, and the minimum is here minus 15.10 volts. And these are very close to what we have calculated. So this is also checked. The next one is about the peak load voltage. That's the light blue one. You see here label 1 and label 2 again, and these are the values in the table. You see also here in the peak what the value should be, because this will give you 15.11 for the maximum, and minimum is 14.96. And if I look at the peak from these two values, that will just maximum minus the minimum give us approximately 0.15 volts, lower than what we wanted, so that's fine. Okay, looking at the peak load current, that is given here in yellow, and again the values for each label are shown here, so 2.014 amps and 1.994 amps, and the peak here is approximately 20 milliamps. Let's go to the peak capacitor current. You see here in dark pink line that has the same shape as the inductor, but it's now leveled at 0, so the average value here is 0. And when you now look at the peak value, will be then 0.19 approximately amps, and the minimum is minus 0.17 or minus 0.18. It not exactly has a mean value or average value of 0, because there are some errors or other simulation issues, but it's close, and the peak here is also close to the 0.375 or 375 milliamps. So now let's jump to the Simulink using the buck converter circuit, and then discuss the waveforms there and how you can generate the plots yourself. So let's now jump to the Simulink itself. Now this is our buck converter in the Simulink. You see here our pulse generator to create a PWM signal. If I click on it, you see here the amplitude of 1 volt, so you can also have here 2 or 3, doesn't matter, just to make it high. This is the period, because we have 100 kilohertz, you need to go 1 over 100,000, so that is your period, 10 to the power minus 5. And our period, the duty cycle was 25%, so this is 25%. We need no phase delay, so it will be 0. So that is our pulse generator. The signal here goes to this switch here, which is an ideal switch. You can click on it. You see also some internal resistances, so they're all very close to 0, so that is close to ideal. This is our DC voltage source, which is 60 volts input. This is our diode, again close to the ideal component, so everything is close to 0 as the on and the forward voltage, again to look at the concept. Our inductor is 300 microhenries, our capacitor is 3.125 microfarads, and our resistor is shown here. So we also measure using the voltmeters and the current meters. Here are currents and voltages. This is for our RMS measurements for our inductor, and this is for the RMS measurement of our capacitor. And here we have displays to display the values. Okay, let's see what we get. And I will now make the scope, so I will double click on it. And you see also how that is generated, the waveform are generated. So let's go here. Now, if I now run this, you can see what's happening. It will take some time maybe, but it depends really on how accurate your measurements are. So if I go like so, the red one is again our inductor current, and the green one is inductor voltage. You see how that is propagating, and the yellow one is our output or load current, and the light blue one is our load voltage, and this dark pink one or almost purple one is our capacitor current. So you see it will take some time depending on how that propagates, again depending on your accuracy. So I will run it and then and speed up the process, and then at some point it will settle down and we will see some details in this plot also. So let me run this faster and then continue with the analysis in the steady state form. So we are now in steady state. Let's first look at the load current and the load voltage. So the yellow one, the load current, and the light blue one is load voltage. You see here the label 1 and label 2, and here we see again 2 amps and 15 volts at the output, so as we wanted. We can zoom in actually in the output voltage here, so we can zoom in here in this part. So let's do that, and then make this full screen in the vertical axis. So you see here exactly as we expected. So we see some wave, some ripple at the output. You see here also from the inductor current, etc. So let's go first to the load voltage only, and then use the two labels and determine now the peak value, and then compare that to the value we have, which is then our 0.15. That was the specification. So if I go down, you see here, so label 2 and label 1, the peak here will be then approximately, now let's say 0.15 volts, but you see in the peak value it is a little bit larger, so it is then here 0.15, now let's say 3, so 153 millivolts. So there's a small error compared to our calculation, so it is very close to what we wanted. Now looking at the inductor waveform here, so let's go to the inductor waveform current. You see the maximum, which is shown here. If I go here with a label 1, you see the maximum, and also here the minimum. But there are also some signal statistics here. You see here the maximum and the minimum, also the peak. You see here the peak is indeed 375 millivolts or milliamps, I mean, very close to what we have calculated actually. But from the peak maximum and the minimum, you can also determine that from the delta y, so the y direction. Also what the peak inductor current must be from the simulator. The green one is our inductor voltage. You see the PWM action here, so it is now 25% of the period is on, and then 75% of the period is off. So this is now the time scale from 0.46 milliseconds to 0.47 milliseconds, which is then 0.01 milliseconds, which is then 10 to the power minus 5 seconds, which is our period. So this did again indeed check. You can also look at it at the maximum and the minimum values for our the inductor voltage. So this is the 1 and this is for 2. You see here it is then 45.04 volts maximum for this, and for the minimum you see here minus 15.07 volts, so also very close to what we have discussed. And but the capacitor current finally, which is our pink one, you see here also the peak value. So here, and this is the maximum and the minimum, and we can see here from the statistic is that the peak capacitor current is also close to the 375 milliamps, so also close to an almost exact same as the peak inductor current. Okay, let's now jump to the TINA-TI simulation analysis and also discuss that in the actual simulator itself also. Alright, in now part 1b, but then using the simulations in TINA-TI Spice. First we will discuss the plots. Again, the same discussion we can apply here. We will use the components we have calculated. We see here the output current of 1.99 amps approximately, so close to 2 amps we wanted. And the output voltage here is 14.85 volts, so a little bit error compared to the 15 volts we wanted. So that's maybe fine for most practical purposes. But let's see what we have in detail. So if I look at the peak output voltage, so we need to zoom in. You see here that the peak output voltage, which is then this one, is 610 millivolts for this capacitor, which is much larger than 150 millivolts. So there's some error here, and that is really because of the practical, more practical components in the SPICE simulator. So what can we do? Now I have tried here or attempted several tunings. So I have looked at my formula, and we know the capacitor value will determine your peak output voltage. So the larger the capacitor value, the lower the delta VO, so the lower the output voltage peak. So I attempted in the first round, so this is now too much, 600 millivolts peak. I said, okay, let's change the capacitor from this value, 3.125 microfarads to 10 microfarads, so almost 3 times larger. What do we have then? Again, the similar plots. You see the VO again, the peak, and this time I have almost 215 millivolts peak. Still way too much. So again, I need to improve. So 10 microfarads is still not enough. The next attempt, as attempt 2, is I made it 20 microfarads. Maybe that's more than required, but let's see what the effect is. So 20 microfarads for the capacitor. Then the peak value here for the output voltage was almost 99 millivolts. So that is perfectly fine. So this is way below our specifications of 115 millivolts. Let's also look at the TINA-TI simulator itself, how we can generate these plots. Alright, this is the circuit in the TINA-TI simulator. You see the DC voltage source. This is the switching transistor, and this is the pulse for the PWM signal, the diode, the inductor we have calculated, and also the capacitor and the resistor. And we measure here the output voltage, and we here measure the output current. This is for the measuring the capacitor current, measuring the inductor current, and measuring the inductor voltage. So let's see what this waveform for the output and others for this capacitor value will be. And we have seen that this is not sufficient for our output voltage ripple specification. Okay, let's see. We go to analysis and then transient analysis, and you plot it, for example, from 0 to 50 milliseconds in order to get the steady state condition, and we have then the following. So we do that. Let's see what we have. Now I will make it larger. What you see here is, let me make a full screen. We will separate the curves, and I don't need the pulse, so I will delete that. You see here, as we have discussed, that indeed I go with I/O almost to 2 amps, so that is close to what we want. And here I see that I will also approach as 15, but now I will again zoom in here and see the actual peak output voltage. Again, zoom in a little bit more so you can see how you can do that also yourself. And then take the cursor and place it on one of the maximum points. Let's say here, this is maybe a maximum point. So let's do this. And the other cursor I will place at the point where I see the minimum. It can be here, it can be there, it doesn't matter. Let's place it here, for example. It doesn't really matter much. Now you see here that 600, now let's say 609 or 610 millivolts, which is again way much, or that is above our 150 millivolts peak output voltage. So we need to adjust this, improve this to get lower than this value. Okay, so we can say let's increase that. We have seen that the 20 microfarads will do the job. So 20 microfarads. So we'll increase that. Why do we increase? Because the larger the capacitor, the lower the output voltage peak. That's what we do. So this is the reason for tuning. You can say I will tune this one, but that will also have an effect on other parameters. So this is the part where you have more control about the output peak voltage. So we only change the capacitor. We do again the analysis, transient, and again the same time span. So you run this, and now we will see that we get what we wanted, as we also have discussed in the presentation before in the plots. So again, separate curves. Let's do that. And you see again the output voltage will approach 2. You can see that more clearly when you use your cursor and place on it. You see 1.95, so that's fine. And this is also in the average. You see that the blue one is for the 40.64. is not good enough. Maybe for some cases, if you want to really precise, you need to really also change that. But this is what we have now, and maybe close to for all practical purposes. And if I now zoom in a little bit more, here is the output, and again zoom in, because I want to now see the peak at the output. And again zoom in. Now take the cursor again and now check the output peak value, and indeed verify that increasing the capacitor will decrease the output ripple voltage. Now I will take this. You see here 102 millivolts as our peak output voltage, which is much smaller than 150 millivolts we are allowed to have for this design. Alright, this was our discussion about the buck converter having the situation in the open loop configuration. We have discussed how we can calculate the component values, the capacitor, inductor, and also the resistor we need as a minimum for our output voltage and output current specification. We also have tuned and specifically looked at the TI spice that we need to adjust or increase your capacitor value we have originally calculated to get the required output voltage ripple. If you have any questions about this, please let me know. I will try to answer them as soon as possible. In the next video, we will discuss the controller design for this buck converter, and we will also work out the calculation step by step there. Don't forget to like and share these videos so that we can reach more people for these interesting topics. See you next time in the next video.